Hey, everybody. Welcome to the webcast. I'm just going to do a quick introduction now that I've remembered to click the button because Jeannie told me. Um, so, Travis is one of our senior consultants. And the only thing I'm going to say is he is actually one of my favorite people. Every single time I talk to Travis, I learn something new. And it's always good. So I hope that you guys get as much enjoyment from this as I will. I'm going to turn it over to you now, Travis.
Perfect. Thank you. So, like Kevin was saying, I'm Travis Phillips. I'm a senior security consultant here at Secure Ideas. And today we're going to be presenting on exploring the Flipper Zero as a hardware hacking tool. So, this is kind of a continuation on a webcast that we've already kind of did, where me and Jennifer, who's another one of our senior security consultants, did a very high level overview of the Flipper Zero, just kind of as what is it as a tool, some of the news and stuff like that it's made. And we gave like a quick, like 30,000 foot view of a bunch of examples, but we didn't really dive into any of them super deep. So the ideal here is I covered some hardware hacking topics, and this time I want to go into those a little bit deeper. So Jennifer will have one that'll kind of cover her examples in more depth coming up in December. So check that out if you're interested. Otherwise, just we'll go ahead and just run through this one. So the Flipper Zero is this little guy. It's basically kind of like a little Tamagotchi pet, but it's basically a small little device. It runs on an ARM processor. It's got a nice lithium battery in it. And it is a very nice self-contained platform for hardware-wise to work on. And it's got an open source firmware. You can build apps for it. And there's already a lot of stuff already built into it that makes it a very useful tool. And while it's got a bunch of radios and infrared receivers and stuff like that, today we're going to be focusing on some of the hardware hacking that you can do with that, which means we're interested in what's up here, the GPIO pins. The GPIO pins are there as well as the USB, which is a USB Type-C connection. The USB Type-C connection allows us to do all sorts of interfacing with the GPIO. So we're going to go ahead and just kind of go into some examples of that. And I originally had 5 prepared, and then I got done with like 3 of these examples and realized I was at like already 45 slides. And the last 2, I didn't want to do a speed run on the DAP link or the SWD. So I decided to trim those out, and I will move those into another presentation because I didn't want to do a speed run. I'd rather just do it as a separate presentation, go for quality, instead of trying to do a speed run through something that's a little bit more of a complicated example. So we've cut it down to these 3, which is a USB to UART bridge, SPI flash programmer, and an ABR programmer. So we'll start off with the USB to UART bridge. The USB to UART bridge, if you're not familiar with UART, it's basically a simple serial interface. Basically, usually it comes in 4 pins. There's a voltage and a ground, and then there's a transmit and a receive. For the Flipper Zero, we usually only need 3 connections, which is going to be the transmit, which is the TX pin, and then the RX, which is the RX pin, and a ground. So the wiring on this is pretty simple. I do have this little diagram here, which shows something that's kind of important. TX does not connect to TX. TX connects to RX on the other side. So you do need to make sure that you cross the TX and RX pins. And one other thing that you'll notice is we do not have a clock signal. So with that said, you need to have kind of an agreed upon speed there for that side. So what is it used for? It can vary. Yes, the Flipper Zero is timeless. And either way, that's just something that kind of comes with the territory of UART. But what is UART even used for? Well, UART is an exposed serial interface on hardware devices, and it can be used for a variety of things. My personal favorite is when it's used for a Linux shell on an embedded Linux system. But it can also be used for like a software interface for like field technicians to have diagnostics, various other things. And it can even be used like for two ICs to be able to communicate with each other. So one example that comes to mind is like some of the 3D printer drivers for the motor drivers can actually be put into UART mode for communication. And then there's a app for this thing that will let you bypass either a master lock or Sentry safe electronic code. And I looked into that one, and it's actually just a UART interface that runs at 4800 baud. And it basically just sends 2 packets to it, and that's it. That's the entire exploit. So that's cool that we've kind of explained it. We've got 4 pins that we're looking for. I wanted to kind of go over finding these in the wild. So on the picture there that we got, the bottom left there, that one was not labeled. I had to kind of like enumerate that one. And this one's also available online. People have already enumerated these. There's that website that I have linked right there. That's the exploiters website. This was a wiki that they started setting up for people that figured out a way to get root on various devices. And a lot of them, they find a UART interface like this, and they'll just map it out and put the pins there. I'll cover how you can do this if you don't have access to that, or like nobody else has enumerated it. On the other hand, we have a picture on the right, and that picture on the right is a console interface, is what it's labeled as, but you can see it's got 4 pins, and they're labeled V, T, R, and G. Voltage, ground, transmit, receive. Not hard to figure out what the pinout is on that one. So on the other hand, if you get one where you don't know what it is, you probably want to start off by trying to identify the pins the best you can. And the easiest way to do that is with some sort of multimeter. Continuity mode is a good one to run in. And the first thing you want to do is try to identify the ground pin. The ground pin is often easy to find. Like if you look at this little image that we have here, I've got this one that's in the red box. If you'll notice there, you've got that like ring around that little pinout hole. And if you'll notice, there's kind of a cross that lets it connect to the ground plane. If that wasn't visible to you, then what you can try to do is try to find a common ground spot, usually where either the barrel plug plugs into the back of the device or something like that, or if it's got USB power, usually the shielding on the USB is grounded. So you can just do a continuity test between those 2 points, and that would help you determine your ground plane. Also, if you'll go back to looking at these images, you'll notice VCC and ground are usually on the outside, and that's a very common trend. So the next would be to identify your VCC. You've already identified the ground. You want to test the other points. And usually what you'll do is you're looking for either a 3.3 or 5 volt consistent whenever you power cycle it to try to get that. You might have 2 pins that'll do that, but generally if I have 2 pins, it'll do that because a lot of times the read pin is high when it's just in a high state. So identify the VCC if you can, and then the TX pin would be the 3rd pin you'd want to identify. And similar to that, you'd have a probe on your ground and then a probe on the other ports, whichever one you wanted to do. And then power cycle it. And usually whenever something's booting up, if that's a UART interface that it communicates with and outputs data to, the transmit pin would start fluctuating in voltage because it's actually sending pulses. So that's something that you can try to identify with that. And then the 3rd or 4th pin would be the RX pin, which we've already potentially identified the other 3. We'll just make an assumption on the 4th one. The other method can be to use a logic analyzer. You can get these little like cheap ones off of like eBay or AliExpress. They're like $10. You can tell it's a logic analyzer because it says it's a logic analyzer. And whoever made this did not want to put their name on it, but it's fine. It works well. But what you can do is you still need to identify the ground pin, which is the easiest pin to identify. But this screenshot here is from PulseView, which is from a tool called SIGROC. The PulseView is the GUI front end for it. And you can just take the other 3 pins that you haven't identified, plug those into channels 0, 1, and 2 on the logic analyzer and do a capture, power cycle the device, and you'll notice pin number or channel number 1 in this screenshot here, we start getting pulses. So that would have identified that as our transmit line for us, even though we don't know what the other two are. The other two, you can see they're raised high, so it's just, yeah, kind of have to guess on that. But like I said, the power and ground are usually on the outsides, so you can do that. And like I said, we also need to determine a baud rate before you can communicate, because there's no clock signal on this one. So determining the baud rate, my recommendation is just to try to brute force some common ones. Usually 115,200 is a good starting one. That's like 90% of the time the right answer. But there's some other common ones there that you can just try whenever you're using your software client to connect to it. And there was a baud rate script that worked really, really well. And it's been ported to Python 3. It was originally a Python 2 script. I had some issues with that one working correctly recently, and I'm not sure why. So you can try that one, but I was getting mixed results with it. And then finally, you can also use a logic analyzer to take like the capture that you got, look for one of the shortest bit flips that you see where it like goes up and then back down, and just measure that out. And measuring that out, you get speed in kilohertz. And what you can do is you can just try to take that, convert that to hertz. So it was 115 kilohertz. We moved it down to that. A common divider, if you'll notice, most of baud rates are divisible by 1200. Just use that and then just divide the hertz by that 1200, floor it. So whatever the decimal is, you round down no matter what it is. And then you multiply that by the common divider, and that would tell you the closest baud rate to that one that you had, which came out to be 115,200, which was actually correct on this instance. So, and if you've got a logic analyzer, you can also attempt like SIGROC as well as any of the other ones, really. Usually we'll have a UART protocol decoder built into it, and you can slap that on there, and usually you have to identify the baud for it. But in this case, I use that baud rate that we identified, and we can actually start to see U-boot 1.1.4, October 1st, 2011. That's a pretty good sign that we actually have the correct baud rate for that. So now we've identified the pinout, we've identified the speed, we got to get wired up. So on top of the flipper, there's actually already pins for this that are already labeled. So you can use the TX and RX pins, which are pins 13 and 14, and they're actually labeled there as TX and RX. And then you need a ground, which can be number 18, number 11, or a number 8. So that would need to be wired up to the hardware device that you're trying to interface to with the Flipper Zero. So we got wires from the Flipper Zero to the device that we want to interface with. And once we've got that, we can plug it into our system via USB. So the point here is that this thing has a serial interface. Our laptop doesn't have a serial interface. We need some sort of bridge, and the Flipper Zero can be that. So once you plug this into your machine, on Linux, you can use LSUSB, and you can actually see that. Now, with this said, you do have to start the USB to UART bridge tool there. And once you start that, that will set it up to be a USB UART interface. If you're not in this, it still offers that, but it's for something different. It's for the Flipper Zero command line application. But once you've got that in there, underneath the dev folder will have TTY ACM0, and that would be the device that I would actually connect a like hyper terminal to. So another little note here, you can access this using sudo or running as root, or you can just make sure that your user account is added to the dial-out group if you're on a Debian-based Linux system, or you use CP if it's an Arch-based system like Manjaro or Black Arch or whatever. As long as you're in that group, log out and then log in, then you don't have to use root access to get to that anymore, because you can see like we've got this little device here and it's owned by this group, so that allows you to access it. As far as the software side, so we've got this thing hooked up to our computer with USB, a bunch of wires running out of it to our device, to that UART interface. We need software to allow us to use the bridge. There's a few choices here. Personally, if I want a GUI-based application, PuTTY actually does it. PuTTY is normally used for SSH, but it does actually support serial. So you can just click on this little radio button for serial, and then you just need to give it the name of the serial device and then the speed that it wants to run at. It's a baud rate. And the other option is screen, GNU screen. Usually people use that for like backgrounding a session. And if you do that, that's fine. But if not, you can actually use it for connecting to a serial interface by just giving it the name of the serial device as well as the speed as arguments. And it will connect to that serial device as long as you have the permissions set. So you can see the GIF that we got here is a screenshot from, or a little screen capture from running that. And you can see I connected to it and then I power cycled the device. We were able to see the U-boot session running, and this is a root shell is what it just dropped me into on this device. And you can do whatever you want on that device from that point. So not bad. Now, I will also tell you too, if you get the baud rate wrong, it'll look a little something like this. I'm doing 9600 instead of the correct one. If you start getting binary gibberish like this, you probably got the wrong baud rate. So doing that again, just connect with the correct one, and we can hit enter a couple of times and we see that we get a /pound. So it is the actual root shell at that point. All right. So any questions on that one before we move on to the next example, which is going to be the SPI Flash Programmer. All right, so SPI actually has a little bit of an introduction to that, if you're not familiar with it. SPI is Serial Peripheral Interface. Serial Peripheral Interface is a rather flexible hardware interface for devices to be able to communicate. It does actually feature a clock signal, which helps dealing with the whole baud rate thing. We don't have to worry about that because there's a clock signal that will tell it the speed that it's communicating at. There's also a few other pins with this one. So there is the chip select pin, which we'll get into in a minute, and the clock signal. And then there's the it's got a few names now. It's Miso Masi was the default one, but there's a few other names, DI. You can do that same thing with SOSI, so forth. Kippo copy. That one's kind of in the air right now because of the fact that they're looking to try to rename it. I think Miso Masi would probably still work if they just renamed it to main and subnode. But the chip select pin is something that's kind of interesting here because there is multiple ways that you can configure this one to run. You've got main and subnodes. And the first one that we have here on the left, this is a bus layout. So we have the clock and then the Miso and Masi, which are input and output pins. The whole point of having the Miso and Masi was to make it so, like with UART, we had to mix or like cross the TX and RX lines. With Miso Masi, it's main in sub out and main out sub in. You don't have to cross those. Miso connects to Miso, Masi connects to Masi. So no mixing. What was nice about that is that this also would allow us to take multiple little peripheral devices that we might want to have communicate with our main would be our main microcontroller unit. And then we might have peripheral ICs that, like temperature, humidity sensor, things like that. These other sensors might support SPI, which would allow us to communicate with them. And what we can do is we can take the IO for in and out, as well as the clock signal line, and turn that into a bus and have all the devices connected to that bus. So those 3 pins are for bus. And then what we'll do is we can have multiple chip select pins. And these chip select pins, so basically 1 chip select pin per device in this configuration. And what we do then is I want to communicate to device number 2. I would take that one, pull that one low, and then I can communicate over the bus. But the second node is the only one that should really be listening to what I'm transmitting, and then so forth. So it allows us to communicate across the bus like that. You can also do this as a one-to-one if you want it to as well. So just connect the chip select to that one-to-one device, and that's fine. And then it also, in some instances, will support a daisy chain layout where you would actually connect the output to the output here, and then you would connect that over to the other one. And you can daisy chain these devices together, which will allow us to have a chip select bridge instead. So instead of the chip selects being the individuals, we'd actually have a bridge. And this would allow you to have 4 pins that would be able to control the entire chain, daisy chain, by using a address. So yeah, that's one option there. So let's see. And then SPI, there's a lot of devices that can connect to it. In this instance, the device that we have is SPI flash. So there is flash memory that supports SPI flash, or the SPI protocol. This is actually very commonly used for BIOS in UEFI, and you can actually use your Flipper Zero to update BIOS or recover from a botched BIOS update. So if you were to brick your motherboard with a failed BIOS update, you can still jump in with this and update it, as long as you got the .bin file for the firmware that's supposed to go onto it. So it's a very common pinout with it. So you can see we've got a chip select pin here at pin number 1. You got your MISO and MOSI's there. Your clock signal here, ground here. We don't need to worry about WP, that's write protect, but you've got your voltage and your ground as well. So with that said, I figured it would be kind of nice to show this little logic analyzer capture. This logic analyzer capture can kind of show you. So you can see the channel number 0 is the clock signal. And if you'll notice, we just pull that down low for the entire transmission of this thing. So there's like 3 packets that kind of get sent here. We are sending a message to it saying, hey, what are you? We're trying to identify this packet. So we would, you can see the clock signal for 4 of these packets. So we send a packet and then it responds with 3 bytes of data. So we'll send some clock signal, and then there's clock signals for all of these bytes that end up coming across. But we started off with the MOSI, which is the main out. So that's us. And we're basically sending a command saying, hey, what are you? What's your ID? And then that chip is responding back to us here on the MISO. And it's telling us, manufacturer ID, the memory type, and the device ID, which this is kind of nice because once we've got our Flipper Zero connected to that, it is actually able to try to attempt to detect what type of chip it's connected to. Now, if there's multiple possibilities there, it might make you select the one that's correct. Like this one here was Winbon memory chip that we had, but it says unknown. That's because there can actually be multiple matches for some of these device IDs. So you might have to specify. The Flipper Zero actually has a application that's called SPI Mem Manager, which will actually allow you to interface to an SPI flash to read it, write it, erase it, compare it to a .bin file that's on your Flipper Zero, and so forth. This is really cool because you can read a flash chip that's SPI compatible and dump the image right to the SD card that's on your Flipper Zero. So the application even includes this nice little wiring diagram, which is awesome. I really love that they just put the wiring reference right into it. But once I was like looking at this, I was like, cool, I want to play around with this. I want to experiment. Let's wire one up. And then that's when I realized pin number 9, which is the 3.3 volts on your Flipper Zero, needs to go over to pin number 3, pin numbers 8 and 7, as well as pin number 1, but on pin number 1, it needs to be run through a 10K ohm resistor. Kind of ugly when you wire it up. I was like, okay, I've got 1 pin here that needs to go to 4 pins on this SPI memory chip. And I would like to do this through a test clip, and I do need to put a 10K ohm resistor in here. So I needed a way to split 1 pin out to 4 different locations and only one of them having an SPI. So yeah, you needed a breadboard. It did work, but I was like, I really don't want to wire this up every time. So I ended up deciding to make a breakout board for it. And it was actually kind of cool because the Flipper Zero documentation actually has the technical drawings here that have measurements and everything like that, that would explain what your measurements need to be to design an external module. So one night in CAD later, and I actually managed to order some PCBs and make a breakout board like this. It would already have the 10K ohm resistor in there, a what is that, IDC connector that you could plug your test clip into, and then you would actually be able to just connect directly to the chip by just connecting a test clip to it. Simplifies the entire process and so forth. You just plug it in, connect your test clip, connect the test clip to the thing, and then you use your SPI memory miniature app. And this is kind of an example of it. You can just go to GPIO, click read. It lets you pick the chip that was there, give it a name, and away we go. And that would create a dump by whatever you named it as on your Flipper Zero's SD card. So I also wanted to throw this out here. B-Sides Jax is this weekend. I will be out there. Just remember this mug. I actually still have a few of these left over, and these are free to a good home. I will also bring out a few of these little flash chips. If you want to test it out, just bring your Flipper along, and I'll be happy to give you one of these little things while supplies last. And you can test it out and practice on this thing. You do not get to keep the flash chips. The PCB is yours. The flash chips are mine. I still have future use for those. All right. So, and then we're kind of moving on to our final example, which is the AVR programmer. So the AVR programmer is usually your Etmel microcontroller. So the Etmega, Ettiny, I believe they're called microchip now. But I had a target that I was like, okay, I want to try this out, but I could have do this with an Arduino, but I had this like old little puzzle board that came from a Raytheon SI CTF afterwards, and it was a pretty cool little toy like that we got afterwards that you could just continue to play with. But you'd plug it in, you'd connect to it over a USB serial, and then it would actually, like, it had a little Tetris game in it, and then it had like a little mud-based game that was kind of like the old Crystal Cave and so forth. But you just basically had a text-based game that you could actually play that was a continuation of the CTF. You'd run through challenges and whatnot and play with it. So, like I said, this is with the Etmel and Etmega microcontrollers. And if you've played with those, like, or played with an Arduino, you might be familiar with something called ISP. ISP is the in-system programmer. The in-system programmer is very similar to the SPI interface. So SPI, ISP. Pretty nice and confusing, except with this, you commonly would see a 6-pin pinout on this one. So you have your VCC and ground. So power and ground are 2 of the pins. We got our MISO and MASU, which is our input and output pins. And then we have a system clock, but we have one additional pin here, which was the reset. So after you're done programming whatever you're going to program into this thing, you usually want to restart it so that way it launches the new code. So with that said, we did have this thing, and we have this little 6-pin header over here, not labeled. So I wanted to try to figure out if this was a in-system programmer interface. So I have a little USB microscope that I like to use, and you can capture pictures of it. And usually I'll just take a regular picture of the device and then just start kind of doing some call outs on some of this stuff if I can. If the chips have silk screenings next to it that would identify like the annotation for this microchip, I would go ahead and just put those into a spreadsheet and start recording some of this data too. But you can take those little like blow up pictures like this, and usually I'll just load them up into an image editor software and just kind of tweak the color values around until you get something that's a little bit easier to read, because these are just laser etched. The text on these are usually just laser etched into them. They're hard to read. So either way, we only had two major chips on this thing. The first one that was here closest to the USB was an FTDI header or a chip. It basically allows you to do USB to serial, kind of like we were doing with the USB to UART bridge. And then we have an Etmega 168A microcontroller. So little AVR microcontroller. Fair enough. So we need to find the mappings for the SPI header, or I'm sorry, the ISP header. There's nothing confusing about those three little letters getting mixed up. So what you want to do, if it's available, is just go ahead and look at the data sheet. And in the instance of this very popular family of microcontrollers, it's absolutely available. So we need to find a VCC and ground that connect to the microchip. So I've kind of already highlighted those. We got this grayish highlight here for the grounds, and then 2 for the VCCs. And then we need those MISO MOSI pins, as well as the system clock, or the serial clock. Those all happen to be on the right-hand corner. So that was nice. And then we need to find the 4th pin from the top here. That would be our reset. And you may notice in this little diagram, you got this circle here. There's 4 of them, but this one kind of has like a little extra ring around it. It's hard to see on these things, but you'll normally see like there's like a dimple on these, and that would indicate where pin 1 is, and reference to the diagram that we have here. So I kind of highlighted on this image here, we need to figure out these 2 here, a common ground plane we can test against, and then we need to figure out where these map to, if they map over here at all. And then same thing with this pin here, if that maps out to this at all. So as it turns out, yes, it does. Again, I just kind of used a multimeter and just use the ohm mode to just kind of test it, because it did run through a couple of little resistors here. But ultimately, once you get done with that, just take a picture of it and start mapping it out. Again, just kind of follow the logic of, let me test for ground first and then VCC, and then we'll do the other pins there. But since I had these mapped out, I could connect a probe to this pin, just push it there, and then just start testing the other pins and just try to figure out where they map to. So after you'd mapped it out, the Flipper Zero application for the AVR flasher actually provides us with a wiring diagram that tells us how we need to wire this up. You can do the ground, and you can have it provide power of 3.3 volts, optionally 5 volts if you want it to as well. The MISO and the MOSI, the SCK, the serial clock, is the one that we need. And then you also have the reset. And once you get that stuff wired up, the Flipper Zero supports a standalone flash and EEPROM dump tool, which used to not just crash my Flipper Zero, but now it actually appears to be working with some firmware updates. So that's awesome. But whenever you start this, it would actually attempt to do an enumeration as well and just say, hey, what are you? And it would actually be able to identify it. Like right here, we can just click that and you can see it actually already identified. This is some sort of Etmega 168 chip. And then it would dump the flash and EEPROM out to the SD card. So on the SD card, I told it to save it as Raytheon SI board. And we ended up with 3 files. One is the EEPROM.hex, flash.hex, and then this AVR file. The AVR file explains kind of it's a metadata file effectively that just says, this is a flipper dump of an AVR, and these are the 2 files that were relevant to the flash and the EEPROM. So, and it also gives you a little bit of information about how the fuses were set on that device. So that's pretty cool. The .hex is the standard .hex that you would normally see that a lot of AVR programmers like to distribute the binary image in. It's basically a text file with some hex, like addresses and hex bytes that would go there. But not only can it be used in this context like this, where we're using it for just doing a raw dump, we can also turn it into a USB ISP programmer, which I thought was actually kind of neat. So you'd be able to use this with tools like AVR Dude, which is a command line tool that you could use a hardware programmer like this to send code to these for programming or reading it or doing whatever you want it to. You'd just select the ISP programmer, and then at that point you'd plug it in. Your computer would actually register it, and you would actually just see it show up. And I thought it was kind of interesting. I ended up with two. Whenever I plugged this in, I ended up with ACM 0 and ACM 1. Just took a little trial and erroring, but I did ultimately end up finding that I wanted to use the ACM 1 as the interface for programming. So AVR Dude, if you're not familiar with it, Arduino actually leverages this for flashing images that you build in Arduino, the Arduino IDE. It would compile and then use this tool to push it to the device. So there's a few switches that you need for that to work. The -P switch, which is the part number, which is the part number reference to the actual microcontroller you're trying to program. Then you need a -C switch, which is the programmer that you're using to interface with that thing or act as the in-system programmer. So in that case, that would be our Flipper 0, but there's a little caveat to that. I found for the Flipper 0, you want to tell it that it's an STK 500V1 programmer, which is a very common programmer. And then the port, you're going to specify the serial interface that you found in the /dev folder. So the /dev tty acm1 for this one. You can use the -in switch if you don't want to write anything. So if you're just reading, recommend it to throw that one in there. And then you got the -u switch, which you can provide multiple times if you want to. And it kind of has a little bit of a weird syntax that I kind of want to look at here. But you got mem type and then colon and then a read write verify flag. The file name of the image that you want to use from your machine. And then optionally another colon followed by the format that you want to use as well. So it supports multiple formats. The default is the Intel hex format, but Flash, usually the memory type would usually either be Flash, EEPROM. There's a few other ones if you check the man page, but those are usually the two you're going to be interested in as a hardware hacker. And then you'd use the just R switch for this if you wanted to do that, or you could use the W if you wanted to write, or a verify if you needed to do a sanity check on this thing's acting kind of weird. Is it possibly bad memory? You can test your image that you already have against what's on this device. So if you're doing a read operation, it would read the data from the chip and dump it to that file. And if you were doing a write, it would use this for the data that it's going to push to the chip. And like I said, you can use multiple. So in this instance, like this would be a example command that would do what the standalone programmer did. And we did the -u for the flash, and then we did a -u for the EEPROM. And if you'll notice, it read the flash chip first and then the EEPROM. The order in which you actually put these multiple switches in will actually be the order that it operates them, does the operations in. So if you want it to read and then write and so forth, like make sure that you do those in the order that you want those to be executed. So overall, that would still just yield that. And I normally liked to go with the raw format, which is one that you can do where it's a raw binary, the -r after the file name. That would just get you a raw binary image of the data. So I wanted to also say too that this presented me with some interesting prospects as a programmer because I used to use this thing. This was a tiny little like I get like a lot of those little like tiny surface mount microcontrollers, and programming those I do like to play with those and use those in projects and whatnot. And I normally don't like to put an SPI header for programming them. Instead, I just use a test clip. And this was the old setup that I had, which just used another little like what is this thing? It's the Arduino Pro Micro that I programmed to be a ISP programmer, which is one of the Arduino examples that you have. and then built a little custom test clip that would plug into the GPIO on that Arduino and allow me to do that. This thing has carried me for a while, and I'm really excited that I can actually just use this thing. And I'm thinking about maybe creating one more PCB on this thing that would allow me to actually kind of just have a test clip that I can plug in and connect to the little tiny microcontrollers. So I'll probably get back to you on that later, but I just want to think some stuff through on that. But yeah, it's potentially a pretty neat little project. Um, so those are kind of the three examples that I had for today's presentation. Uh, it does do a lot. I'm still very impressed with this thing, but overall, it does actually feel as a stopgap for a lot of things. But there's still a few gaps that you might have. Like this thing is not a logic analyzer. It's not a JTagulator yet. I think it could actually have potential to be one. And it's also not a universal programmer. Like we did an example where we did an SPI flash chip, and we also did an AVR. We did an AVR device, but there's a lot of other like memory chips and stuff like that that it's not going to be able to fill. So you'll still need to get some of those, but I did find that this fills a lot of the toolkit that I use, and I find myself increasingly going for it over and over. So like this has become my new USB to UART bridge. I do have a little one, but I don't really use it anymore because this actually already has a nice little carrying case. It's already there. It's nice and fast. Um, a lot of other little tools as well, but like it's absolutely a tool worth looking into if you want. It's about a 170, I think is the price point for it, but it already covers quite a bit of hardware hacking. And on top of the SPI, there's a bunch of other little projects that people have done because there's other interfaces like I2C and stuff like that, which the STM32 microcontroller that's in this actually supports. So people have gotten it so it works as like a GPS receiver and stuff like that. So it's definitely something worth playing with. And hopefully in the next presentation, the part 2, we're going to cover doing a little bit of stuff with SWD, which is serial wire debugging for ARM, as well as JTAG, which these are two little protocols that will give you direct hardware access or direct access to the hardware for debugging purposes, which that's going to be in the next one. So with that said, I'll open the floor. Do we have any questions?
Man, that was a lot of fun. I'm waiting for questions. I just wanted to tell you, I really enjoyed that. I don't play that much with hardware anymore, and I need to get one of the flippers.
You do need to get a flipper. So like I was saying too, like you had the 115,200 baud rate. If you don't have it in the USB UART bridge, you end up getting into a flipper command line application for controlling this thing. And I've been wanting to play with something that I noticed in there, which is the chat. If it has a chat function that will start a chat server running at 443 megahertz and allow the devices to communicate basically using a TTY over radio. And I'm like,
oh man,
I want to play with that. I just have to have somebody else that's nearby that actually happens to have a flipper that wants to do a chat with me.
Nice. Yeah. So one of the question coming in from Aaron Clark. So one of the functions on the flipper is to record and playback signals. What types of applications could that function be used for in the context of device hacking?
So not necessarily capturing signals. Like most of the examples that we gave today was, so the first one was the UART. We are actually interfacing with it. And then the other two, we were actually using it to dump code or data from devices. So in the instance of the SPI Flash and AVR programmer, we are going to want to just dump and pull firmware off these devices. So like I was showing with this thing, I got this from somebody that Raytheon SI. This is a CTF board. I have no idea what the firmware is on it. But with the third example that we did there was the AVR programmer, I can get the firmware off of this device and then start hacking on that and reverse engineering it in Gahedra or whatever you want to do. This provides us with a mechanism for dumping firmware. So we can use that for analysis and looking for other attacks that we want to do against the firmware. or we can just completely hack it, because that's a pretty nice little microcontroller there, pretty well documented, and I could reprogram this thing to do whatever I want it to do. In fact, the welcome screen that was on that example, they actually were like, hey, by the way, if you do end up doing some hardware hacks, why don't you send us an email and tell us what you did with it, because we'd just be interested in it because it's fun and nerdy. So that's something that you could do. UART is an interface that would allow us to interact with whatever was on that serial interface. And like I was showing with the example with this little Pogo plug, it was a actual Linux shell. So this would be almost similar to being SSH'd into it and being able to interact with it. Except instead of doing that over the network, we're doing it through jumper cables and a flipper zero. And that's a pretty common interface that you'll see in devices. Like I said, if you go to that Exploiters website, they have an entire wiki of several devices. And they have the UART pinned out, and they're like, yeah, it's just a shell. If you just connect to the UART, you just get a root shell. Enjoy. There was also on one of the slides that I had with that, if we go back to it, I dumped the shadow and the Etsy password on it. And if you'll notice, that was the only user on that system was root. So if you can use, and you can also use it, so if I wanted to, I could start up Telenet D or something like that, and then remote into this thing across the network. But I can actually read and dump the memory off this device to get the firmware to look for vulnerabilities that might be in the web application that this thing serves up, or any of the other services that it tries to render. And like at that point, it's almost more like you're a forensics investigation that's malicious, looking for vulnerabilities inside of a file system image. So, and if you check out the exploiters website on this particular device, yeah, they also found a command execution vulnerability in the web app. If you exploit that web app, you're now sitting as a root user on a Linux device that is embedded, obviously doesn't have EDR installed on it. And this is the beauty of embedded devices. You can't install antivirus on this. You can't install EDR if it doesn't ship with it, which if it does ship with it, it's not for you. It's for the company that made it. Yeah, you're sitting with root access on a Linux system that's headless on somebody's network. That is beautiful. So it's not a bad place to be. No. So, but that's what the UART does, is it allows us to interface with these sort of things. So the Flipper Zero does allow you to interact with the UART interface and so forth, but
yeah. The next question isn't for you, it's just in general. It's a question about the CPE certificate is related to ISC squared. It's not. It is a certificate to just to attest that you attended an hour-long presentation, and whatever professional organization you belong to that may require that. Aaron mentions ISC squared and other certifications, but we also see quite often where organizations want proof that as an employee you've attended continuing education. That's all that is. If you don't have a requirement, or you don't know of a requirement, don't bother. But if you have a requirement, for example, I have my CISSP, I have to collect 120 hours of training over, I think it's a 3-year period, but it might be a year. I don't remember. So that's what that is. So awesome. Any other questions for Travis while we're here? Okay.
I have a question. Anyone going to B-Sides?
Yeah, I was going to say, we're going to be at B-Sides Jack's this weekend. I'll be in Pensacola the week after for a conference. If you're going to be in Nashville for ISC Squared Security Congress, we're having the fanciest vendor dinner you'll ever see at a Waffle House at 10 p.m. Mainly because I decided that fancy vendor dinners were boring and let's do something funny as a joke, and then my team ran with it. Or we'll be at AppSec DC for the Global OWASP meeting, where they're announcing who won the board seats. I will be there as well. Maybe having won the board seat. So awesome.
Don't forget,
the voting has not started, Aaron. Sorry, Travis. I started to answer a question.
Okay. I was going to say, don't forget, if you run into me at B-Sides, let me know if you're interested in one of these, and let's chat.
Awesome. Thank you very much, everybody. Travis, great work as always. Thank you very much.
Thank you guys for showing up.